Good morning.
Good morning.
Well, the weather's going to be sort of cold and nasty, and so nothing better to do than Fourier transforms, right?
Yeah.
So we're going to give you an even broader toolkit today, talking about comb basis sets. Actually, I do not expect we will get to lock-in amplification, gated integration, and autocorrelation today, but those will likely be the next topics that we will start in on next week on Tuesday. So, start with comb basis sets. So, I'm actually just going to give combs are really easy to describe in terms of Fourier transform pairs, so we're really going to spend most of our time working through a couple of problems on combs. And then if time permits, we'll relate these back to modulated signals. Because a comb can be used to describe a digitizer, and a periodic signal can be used, also can be described by a comb basis set. Now you have no idea when I'm talking about a comb, but you know what a comb looks like, right? Comb looks... Oh, come on. Oh, I know what I need to do. It's working fine. I just don't have it here. There we go.
Is this recording too?
I sure hope so. Yep, recording.
Oh, they're still off.
Oh, here's the wrong one. Comb, right? And in our house, my daughter has long hair, so there's lots of those things in it too. At any rate, the comb basis set is really one in which you've got a series of impulses. An infinite series of impulses. 0, T0, 2, T0, etc. ... And that Fourier transforms to a comb. With F0 equaling 1 over T0. That's a comb. Just to give you an example of what I mean, if you take, and if you were to digitize a signal on an oscilloscope, what you're doing is effectively taking your signal and multiplying by a comb. Because it's going to be evaluating the integral over each of these impulses is 1. So it's going to be integrating over the impulse and your signal at that one particular value. It'll just be recording that value. So that's one way that combs show up. Anytime you have a repeating signal, it can also find its way into a comb. For example, if you have the convolution with a comb and a Gaussian, then you have a train of Gaussian pulses. So a function generator you can think of as being something that can build a comb, which you can then use in other instruments, for example. All right, that's my lecture today on combs. Pretty exciting, huh? Let's go ahead and do a problem. Let's consider this case where you have a truncated comb of rectangles. So our comb function does not exist from negative infinity to infinity, alas. We have some finite start and stop on this, and the start and stop, we're doing a 100-second acquisition. And the comb has these rectangles that are 1/10 of a second wide, spaced every second. What is the Fourier transform of this? Ponder it. I'm going to go ahead and turn off the recording because there's nothing else to record now except your thoughts. And those are silent if they're still kept inside your head. So release them to the people around you. Chat. Ponder. All these household products.